Okay, good morning. I am once again excited to be with you. This is,
So good.
as I've told you before, one of my very, very favorite topics, and today's lecture is one of my very favorite. So, on Tuesday, we forgot to have an opening prayer, and I felt like at the end of that lecture, some of us went away a little bit confused. So I think maybe we need to invoke the Spirit today. Would anyone be willing to help us with that? Get us started in the right way. Yes, thank you.
Father, given the opportunity to BYU, that it was something that's given to us and that everyone has. We ask the Father that maybe to honor this opportunity, this chance. And we will discuss it and they may benefit in our mission to serve others, to share outside of Christ. Father, we ask you for a blessing on the instructor, but also be called to teach. We ask that he may be able to edify us in the Spirit. Knowledge of the physics to be able to be inspired with purpose to explain the particular topics. We ask you, Father, that we to maybe receptive to the Spirit, that we to receive the words and be able to allow to have better understanding. We ask you for a blessing on these things as well as our classmates. Thank you. In the name of Jesus Christ. Amen.
Amen. Thank you. We're going to talk about RC circuits today. And the R just stands for resistance, like a bulb, and the C stands for capacitor. We've talked about capacitors before, but now we're actually going to put them in a circuit. Now, Greg, I really don't think that I'm ever going to do that. Okay, I think I'm going to go through my life without ever putting a capacitor in a circuit. Why would I? Okay, well, it turns out that in any circuit that's analog, by that I mean it doesn't have those high-tech integrated circuits, there's only a handful of elements that they're made of. If you look at an old-timey stereo, you got resistors, you got switches, you've got capacitors, and you've got inductors. We're going to talk about inductors, which is just a coil, later in the semester, but you're dealing with one of the four elements, and so it seems like that would be an important part. Now, this is one of your homework problems that I'm hoping to prepare you to solve today as we go through the lecture. Come on. Okay. Let me just remind you that the next exam opens a week from tomorrow, on the 21st. And I've already posted 2 sample exams with their solutions to the MAC site. And I'm going to have a review session next Thursday evening before the exam opens. It will be in this room here at 7 o'clock, and that will be recorded. I just want to encourage you to be patient with yourself. Until this clicks, until it just falls into place, it all seems confusing. And I didn't understand circuits until I was much, much older than you are. I had already been through my undergraduate degree, my graduate degree, and I'd already worked at Lawrence Livermore Labs. And then I was on my second postdoc with Lillian McDermott before it suddenly just, had the aha. And so you need to be patient with yourself and let yourself have that aha. But please have it before next Friday. Okay. And if next week, as we're getting close to Friday, you still haven't had the aha, you need to see somebody. Okay. You need to see a doctor. And I am a doctor. as my children say, just not the kind that can actually help anybody. So, okay. I got this email. Greg, I'm in your 106 class. That's a lie. This person was at Montana State University years ago, and it was a 206 class because everything's inflated there. And I used to have a grasp of what would make a bulb brighter. After I learned the voltage model, I'm completely lost. Anyone resonate with that statement right there?
Yeah.
Okay, yeah, don't raise your hand. Okay. Current will take the path of least resistance, so the bulb that sees more current will be brighter. I understand this to mean less resistance, more glow. In the voltage model, there will be a higher voltage drop over the bulb with more resistance. I understand this to mean more resistance, more glow. To my brain, this seems to be a contradiction. I know the error is in the way I am thinking about this. That shows maturity, that maybe I'm wrong. I know the error is in the way I'm thinking about this, but I can't seem to find it. If you could help get me back on course, that would be great. Thanks, Jason. Okay, let me see if I can help. If we kind of look at different circuits, we have some circuits that have networks in parallel, but not parallel across the battery. And then we have networks that are parallel across the battery. And then finally, we have networks that are in series. Now, if I use V equals IR, I know that across parallel networks, the voltage has to stay the same. And that's true down here as well. It's just down here, the voltage across A and B is the battery voltage. And here it's the same, but it's less than the battery voltage. And so if I have, I'm just going to make the assumption that A has the big resistance and B has the little resistance. The current, if the voltage or the push is the same from here to here across each of those branches, I'm going to get more current flowing the easy path. Okay. Now, if I do the same thing over here with V equals IR, what's the same for both A and B? Well, it's the current. Once it goes through A, it has to go through B. So this is the same for A and B. And so that means if I have a big resistance here and a little resistance there, I'm going to get a big voltage difference here and a little voltage difference there. Everyone with me? Yes.
We can't see the bottom diagram on the left side.
Ah. Okay. I've run out of board space, so on the back of that. Who's going to be a helper here? Thank you. Okay. Mr. Rogers says, look for the helpers. Look for the helpers. Okay. Now, where's the logical flaw in Jason's reasoning? Well, he says, in the voltage model, there will be a higher voltage drop over the bulb with more resistance. Well, we are always using identical bulbs. And so there isn't a bulb with more resistance. It doesn't exist in this class, okay? And so if I have one bulb in B, I can't just have one bulb in A, otherwise the boxes would have the same resistance in them. So let's say I've got two bulbs in series in A. Well, would that be more resistance? Yeah. But now it's the same box A and the same box B. So I've got two bulbs here and only one bulb there. This has twice the resistance of that. And so when I divide up the 12 volts of the battery, I'm going to get 4 volts here and 8 volts here. But that 8 volts across this box of A is just going to be 4 volts across here and 4 volts across there, right? And so everything's consistent. I don't have a bulb suddenly changing whether it's brighter or dimmer, depending on how I hook it up. See if your neighbor followed that reasoning. See if your neighbor's okay. Do a buddy check.
Well, something that it means that the current is dependent on resistance, but the voltage is not. So like, the R, the more resistance is gonna have more voltage because it requires. Rather, but the current, the one less.
Sorry.
Dependent on.
I think so, yeah, because then they're gonna be a pair, they're parallel each other, but they're adding a serial resistance to that.
Yeah.
That would be the. So.
Can I mess things up, Oliver? Okay, are there questions?
Yeah.
Okay. Let's help you with your tutorial homework. We started this problem on Tuesday. Let's finish it up. What we found was that we could easily rank the bulbs using the current model. We just said that all the current has to flow through 6. Then it splits 50-50 between 4 and 5. Then the river comes back together and then it splits not 50-50, but some other way, with more than half going through 3 and less through 1 and 2. And so what that ranking looks like is 6 is brighter than 3, which is brighter than 4 equals 5, which is brighter than 1 equals 2. Now, we found that when we tried to use the voltage model to rank the bulbs, we ran into trouble. First of all, we have to put things in boxes that are in series with each other. And 6 is in series with the network of 4 and 5. And it's then in series with the network of 1, 2, and 3. And when we divide up the battery voltage, we have to ask ourselves which of those boxes is the hardest to get through. Because the battery's got to use up its 12 volts of pushing coulombs through those boxes. And the one that's hardest to get through is going to get the bigger share of the okay, and it's that bottom box that has the most resistance. And then the top box is second and the middle box is last. And so it's a papa bear, mama bear, baby bear situation. Now, does that give us the same answer? Well, 6 has all the voltage across this box, And so since that's the most voltage, I would get 6 as the brightest. 3 has all the voltage across its box, and since that's the second biggest voltage, that would be the next brightest of the circuits. I know that 3 has more volts across it than 4. And 4 and 5 have to be equal. So far, it's looking pretty good. But when I try to put bulb 1 and 2 in there, I got a pizza problem. 1 has half of the volts across the top box, half of a medium pizza, if you will, whereas 4 has all of the volts across the small, the smallest voltage, the small pizza, if you will. So I'm comparing half of a medium pizza to all of a large, all of a small pizza, and I can't do that. So I know that 1 has to equal 2, and it has to be 1/2 of whatever I have for 3. Okay? But I don't know how much bigger 3 is than 4 and 5. And so I don't know whether to put these guys in here or back here. Well, I know because I've got a second model. I've got the current model. But if I only had the voltage model, I would be stuck. I would have a pizza problem. Any questions on that? You see the pizza? Okay. Now, fortunately, you can jump back and forth between models. If I can say, using the current model, that 4 is brighter than 1, then I can definitely say that the voltage across 4 is bigger than the voltage across 1, because we have that in our toolbox. More volt, more jolt. The more volts across a bulb, the brighter it is. Okay? Now, suppose we take out bulb 1 and leave the empty socket behind, and that leaves a gaping hole there. What's that going to do to bulb 2? Yeah, it goes out. It's on an incomplete path. And so it is dark. It is dark. What happens to the resistance of the boxes? Well, I didn't change the bottom 2 boxes, but the top box now looks like the bottom box, okay? Because this is no longer a path. Now, if we want to know what happens to bulb 6, we're tempted to say, well, what happens to the resistance in the last box? Well, nothing really, okay? But that's the wrong question. That question will never get you the right answer. What you want to ask is what happened to box 6's share of the total resistance, okay? If the top box suddenly gets more resistive, well, the total resistance in the circuit just got bigger. And even though 6's resistance didn't change, its share got smaller. Its share got smaller. So we need to be careful with our words. If I have 2 ohms in series with 4 ohms, and I want to share these 12 volts, well, this is twice as hard as that. And so I would share it 4 volts and 8 volts. Now, if I say, and if I believe, the greater the resistance, the greater the voltage, well then, what about this? I got 200 ohms here. That's 100 times bigger than that resistance. If I believe this, the greater the resistance, the greater the voltage, this should get 400 volts. That's pretty impressive from a 12-volt battery, wouldn't you say? So what question would you ask me? What question's burning in your mind right now? Yeah, what's this resistor sharing the 12 volts with? If it's another 200 ohms, then it's going to share it 50-50, 6 and 6. It depends on what you're sharing it with, okay? And so what we want to say is the greater the share of the resistance, the greater the share of the voltage. Okay? So let's go back here. Bulb 6's resistance didn't change, but its share of the total changed, okay? If let's say, okay, let's add up all the money that Miriam and I have, okay? And we find that Greg has 60% of the money. That's because he's old, stinky old, okay? But then tomorrow, Miriam inherits $1 million, okay? And now suddenly, my share of the total wealth between the two of us went down less than 60%, even though the money in my bank account didn't change. Are we all understanding what the share means? Okay, congratulations, Miriam. Okay, pay your taxes.
Dang it.
So 6's share of the total resistance goes down, so its share of the 12 volts go down, and that means that it gets dimmer. It gets dimmer by the voltage model. Now, we can also do that with the current model. With the current model, I removed a path by taking out this bulb 1. That's going to increase the resistance, finish your sentence, of the circuit, and that's going to decrease the current, finish your sentence, through the battery. And since 6 is an indicator bulb, its current is going to go down as well. And so 6 gets dimmer, whether you're arguing with the voltage model or with the current model. Do a quick buddy check. Do a quick buddy check. I just did your homework for you. You're welcome.
All the time going through it, therefore the high terms is called this. That was right at the beginning.
Well, if you think about it, like current models, like now it's 3 and technically just like 1 now. So. It's a good time.
Picture of the down. Because now, oh,
Increases match.
the 3 should be bigger.
Are there questions on this problem? Yes, sir. I didn't hear. Oh, no. 4 and 5 each get exactly half of what goes through 6. And if 6 gets dimmer, they have to get dimmer as well. And if we use the same argument, but now instead of just me and Miriam in this story, there's 3 of us. You know, if Miriam inherits $1 million, both of the other people have a smaller share. Okay?
Yeah.
Now, what happens to the first box's share of total resistance? Okay? In other words, what happens to bulb 3? Well, let's back up a minute. If I were to use the current model, I'd get a pizza problem. 3 was getting more than half of a large current through bulb 6. Now it's getting all of the current through a dimmer bulb 6, a smaller current. So the amount of current in the battery went down, but 3's share of it went up from more than half to all of it. Pizza. But if I use the voltage model, if this box is getting a smaller share and this box is getting a smaller share of the 12 volts, this box is getting a bigger share of the 12 volts. 3 has to get brighter. Okay. Now, the way I would argue that, if I wanted to do it mathematically, is I would pick a path that went through 3 from one side of the battery to the other. 3 plus 5 plus 6 has to add up to the 12 volts of the battery. I know that this one decreases. I know that this one decreases. If it's still going to add up to 12 volts, this one has to increase. Okay? So the voltage across 3 will increase and it will get brighter. Now, I've got a clicker question for you, kind of a pop quiz, if you will. Everyone get your clicker out. I'm really hoping that we all get this right. Okay, this is gonna make me sleep better tonight if you all get this right.
Could still be equal to 6.
I have this circuit and we have these resistors hooked up as shown, a 4, a 3, and a 6. And if I measure the voltage across the 6 ohm resistor and find that it is 4 volts, what am I going to measure across the 3 ohm resistor? Which of those is it? Again, this is not meant to be difficult, it's meant to be easy.
Said that, I know that this is talking about but he said yesterday that when they're the same parallel, that has to be the same. Like, they're equal, whatever.
Okay, last call. Everyone get your vote in.
Oh, no.
Okay. That's not quite what I had hoped for, but we'll take it. Okay. The answer is C. Okay. Now, any paths that are parallel, okay, if you can start and end at the same location, any path has to come down the same number of meters on a mountain or volts in a circuit. Okay, I have to drop the same number of volts. And so that's got to be 4 volts. Now, what's the voltage across the 4 ohm? Well, it's got to be, it's got to add up to 12, so that's got to be 8. Now, this is perhaps the most important question you'll be asked today. Did the 8 volts split in half at the node? Yes or no? No or heck no? Heck no. Heck no. Heck no. The volts don't go anywhere. They can't split because they don't go. Okay? And so I can prove that those are not splitting there by changing this a little bit. If I add one more resistor there, what I'm going to find is that the voltage across the 4 ohm is 9.6 if I measure it. And across the 6 ohm, it's going to be 2.4, 2.4, 2.4. And if you multiply 2.4 times 3, do you get 9.6? No, no, you don't. And so clearly the 9.6 is not splitting. Now, how do I get these numbers 2.4 and 9.6? Well, I put things in boxes that are in series with each other. And what I find is that the resistance of the top box is 4 ohms. That's obvious. Well, the resistance of this parallel network has to be less than the least. And we're going to show in a little bit later in the lecture that the resistance of this box is 1 ohm. That box is 4 times harder to get through than this box. And 9.6 is 4 times bigger than 2.4. And it adds up to 12. Okay? Check on your neighbor again.
each path. Yeah, but like. Five, like, so like from 4 to 6, I'm 4 to 3, and 4 to 2. They all have a 12.
Okay,
So it's not like.
another clicker question. This one more challenging. I have this circuit with 2 bulbs and a switch, and we want to know what is the voltage difference from point A to point B. You can click now. Your choices are 0, 3, 6, 12, or none of the above.
Because it can't be removed, it has to stay.
Maybe close.
It might be 0 too, because, you know,
The answer is it's.
it doesn't matter what direction you go.
Okay, last call. Okay, 0 volts is the winner, Unfortunately, that's not the right answer. The correct answer is 12 volts.
This better be a good side.
12 volts. Okay. Well, how can that be? I got a break in the circuit. There's no current. How can there be voltage? Well, remember when I say voltage, I mean voltage difference from point A to point B. And if I look at those bulbs, there's 0 volts across that dark bulb. There's 0 volts across that dark bulb. And it's got to add up to 12. It turns out that the voltage rises and drops must be equal around any loop. I didn't say any closed loop. Any loop. Any loop. Any loop. Now, since this is 0 volts, the voltage across the switch, the open switch, plus the voltage across this dark bulb has to add up to the battery voltage of 12. That means the voltage across the open switch must be 12 volts. Now I can show that. If I measure the voltage, I've got these 3 bulbs here. And if I measure the voltage across these from a 12-volt battery, I would get 4, 4, and 4. But if I take this bulb out and leave a gaping hole there, okay, just leave like the open switch, what I would get here, if there's any justice in the universe, is 12. Oh, come on. Okay, let's try that again. Oh, better than 12. Ha ha. 12.7473. And if I measure it across the battery, what I get is, come on. What does it say? 12.73? Oh, okay. Life is good. Now, wait a minute, Greg. When you put the leads of that voltmeter from here to here, you were kind of completing the circuit. So maybe there weren't 12 volts across that empty socket before you put the voltmeter there. Maybe your measuring it changed it. Well, let me see if I can dissuade you from that idea. Suppose I had 3 equal resistors, each 10 ohms, in series with each other. The equivalent resistance would be 30 ohms, and if I use V equals IR, that's going to give me, it's going to give me 0.4 amps through that battery. And clearly, I would divide the 12 volts up evenly, 4 volts, 4 volts, and 4 volts, would I not? Well, what if I were to change this middle resistor to 1,000 ohms? 1,000 ohms. Well, now what I find is that I only have 1/10 of a volt across the two little resistors. They're easy to get through. Most of the oomph of the battery is used across that 1,000 ohms. I also find that the current through the battery is now only 0.012 amps if I use V equals IR. Well, what if I want to go big? What if instead of 1,000, I go 1,000,000? Okay, 1,000,000. Well, now, this is essentially, if I'm honest with myself, all of the resistance in the circuit. That 10 and that 10, that's pocket limp, okay? And so I'm going to get almost all of the 12 volts across this big, huge resistance. And I'm only going to get 1.4 times 10 to the minus 7 amps through that battery, okay? Barely a trickle. Now, if I make the jump from 1,000,000 to infinite, and that's what an open switch or an empty socket is infinite. Well, now I have exactly 12. All of the voltage is here. Now, and I get 0 amps going through. Well, is there really 12 volts there, even when I don't have the voltmeter? And the answer is yes. You remember that with 30,000 volts, we could push a spark through 1 centimeter of dry air. And so if this gaping hole here was 1 centimeter wide, and I could turn a magic knob here to increase the strength of the battery, make it bigger, make it bigger, make it bigger. When I got to 30,000 volts, I would throw a spark across that gap. So there is a pressure difference trying to make the current go, but it can't do it until I get enough push to jump the gap, okay? And so with air in there, it's not really infinite resistance, but almost. See if your neighbor is now on the bus.
It's like the current can't stop. But voltage can because it said voltage can, but the current can't. Like voltage doesn't, it's just there. No, yeah, but current needs to have. Oh, no, yeah.
Okay. Another question with your clickers. I have 4 identical bulbs that are connected to a 12-volt battery as shown. If bulb 2 is removed from the socket, leaving the socket, the empty socket behind, what voltage would you measure across that empty socket? And your choices are 12 volts, 9 volts, 8 volts, 6 volts, 0 volts. Go ahead with your clicker.
But that's only because I think it's 1 and 2 are parallel and have them just split it up. Like there's in series, so it's 6 by 6. We just said it was have one voltage. And I think 2, 3, and 4 were trying. 3 and 4 have together. Not thinking if we're. You said also depends if.
Okay, last call. Get your vote in. Good. We seem confused. We seem confused. Okay, the correct answer is 8. Whoa, why 8? Well, there's a general rule that if you want to learn something about the sun, the most important thing is what? Do not look directly at the sun. Okay, that's going to blind you. Look away from the sun and find some other way of observing the sun. Okay, and it's the same thing with sockets. If I want to know what the voltage is across this empty socket at 2, look away from the sun, look away from 2 to the other branch, If 2 is now a gaping hole, all the current that goes through 1 has to go where? Through 3 and 4. They are now in series. They're equally dim. And so that's going to be 4 volts, 4 volts, and 4 volts. Now, if it's 4 volts across this bulb and 4 volts across that bulb, across this branch is 8 volts. And across that branch must be the same because they're parallel. So it has to be 8 volts. Quick neighbor check. Just a second.
Is there a way to calculate what the voltage drop across 1 would be before the 2 is removed?
I can't hear you. What did he say?
The voltage drop across 1 before two.
If I ask what the brightness of 1 is compared to 3, how would you answer that?
Brighter.
Would it be? With 2 out, so nothing can
No,
go.
before 2 is out.
Oh, before I take 2 out, 1 is brighter than 3 and 4, and so 1 would have more than 6 volts. But afterwards, they all have 4 volts. Okay. I'm sorry, I didn't understand your question. Old deaf guy. Okay. Well, that was fun. And that sets us up for a new idea. And that is, we're going to try to understand this capacitor here. I went down to an auto stereo store, and back in the day when people would come through with stereos that would wake up the neighborhood, they needed these capacitors, and that's the only way you can find them these days. So I'm going to ask you some philosophical questions. Suppose I went down and got 2 identical 12-volt batteries, and I hooked them up this way with the positive up and the positive up in that diagram. How bright is that bulb? It's dark, because this battery is trying to push conventional current clockwise, and this one's trying to push conventional current counterclockwise. They're fighting each other, and I got nothing glowing in that bulb. So my philosophical question, is this the same? I got 12 volts here, I got 12 volts there, I got a dark bulb. It's similar, okay? The only difference is that here, the 12 volts is being caused by chemistry, and here it's being caused by physics, okay? Not a big difference. Chemistry is just applied physics. You can tell them I said so. Okay. Now, suppose I can't afford 2 12-volt batteries. So I go down and I buy a 12-volt battery and a 0-volt battery. Give me a 0-volt battery. Why don't you just throw it in free? Okay. How bright's that bulb going to be?
Very bright.
Yeah, 12 volts bright. 12 volts bright. They're fighting each other, but this one isn't fighting very much, right? Now, my philosophical question is this the same with a closed switch? I got 12 volts there, I got 0 volts there, I got a bright bulb. Pretty similar, okay? Now, let's talk about this circuit where I have a switch, a bulb, and a 1/2 farad capacitor. This one happens to be a 1.5 farad capacitor. And originally the capacitor is empty. And I made sure it was empty by hooking the positive terminal through this bulb to the negative terminal to make sure that it had been discharged. Okay. Now, if I remember how capacitors work, it's through this formula here. The definition of capacitance was how much charge you could store before you increase the voltage by 1 volt. But if I cross multiply, I get this equation here. So what you see from that is this voltage across the capacitor can change depending on how much charge is stored in it. If it's empty, its voltage is 0. And if I were to measure the voltage across these terminals right now, I would get 0 volts. But as I store charge in it, as Q gets bigger and bigger, the voltage across these terminals gets bigger and bigger. It's like a variable strength battery, okay? Now, because it's empty, it starts out with 0 volts. And with that switch open, this bulb is dark, and a dark bulb has 0 volts. Well, where's the 12 volts of the battery? I got to have a drop equal to the rise of the battery. The 12 volts have to be across that switch, okay? Now, as soon as I close that switch, I have 0 volts across that switch. Where's the 12 volts now? Well, it takes time to charge up a capacitor. That's going to take for this one about 3 seconds. And when I first close the switch, it's still empty. It's still got 0 volts. So now the 12 volts is all across that bulb, and it suddenly is bright, 12 volts bright. And that means that there's flow going through that bulb. Well, that flow is charging up the capacitor. I get positive charge on the plate that's closest to the positive side of the battery, negative on the plate that's closest to the negative side. Now, how does that happen in real life if I really believe in electrons? Well, instead of conventional current going this way, I would have electron current going the other way. And so what we're doing is we're stealing electrons off of this plate through the battery and dumping them on that plate, okay? And in the process, those electrons going through the bulb are heating it up and making it glow. Now, once I get enough charge on here that this is charged up to 4 volts, because this is not 0 anymore, now the bulb only has 8 volts across it. It's dimmer. And that means the current going through it is smaller. But it's still current going to charge up the capacitor. And so it charges up even more until it's 8 volts. And now that bulb is only 4 volts. It's even dimmer. And the current through the bulb is even smaller. Now, eventually, I get that voltage across the capacitor up to 12 volts. And now there's nothing left for the bulb, but it goes dark. And so I can make that bulb go dark slowly. Let's see that in real life. Okay, I'm going to okay, so I put the negative terminal of the battery there, and I don't have a switch, but the closing of the switch will be me connecting the positive terminal here. And watch what happens to the bulb. 1, 2, 3, go. Now, folks, that's not the first time you've seen that. If you've got a fairly recent model car, anytime you get in the car and close the door, it does that. Indeed, any system that has an analog timing device in it has a capacitor in it to essentially make things either go brighter or go dimmer as a function of time. as a function of time. Okay. Questions on that, what we just saw? Next week's tutorial is on RC circuits, and we will be playing with RC circuits. By we, I mean I'll be playing with them with the camera rolling, and then you'll be sort of voyeuristic watching me having fun with the RC circuits. Okay, now let's move on. What if now with that that capacitor all charged up, I open the switch, and I did. What voltage do I have across that switch now? I got a 12-volt rise across the battery. I got a 12-volt drop across the capacitor. Do I need anything across the switch? No, there's 0 volts across the switch. Unless I take out that battery. If I remove the battery, how? Now this looks like a battery. It looks like a 12-volt battery. And it's trying to push conventional current counterclockwise. But it can't because of this open switch. So now I have a 12-volt drop across that open switch. Until I close the switch, now it's just 0 volts. And so now the 12 volts has to be across the bulb. And it's super duper bright, 12 volts bright. And that means I've got flow going through that bulb. Now it's going counterclockwise. I'm discharging the capacitor. And when I get enough charge off of that capacitor that it's now only 8 volts, the bulb is only 8 volts bright. And then it's only 4 volts bright. And then it's 0 volts bright. And now the capacitor is empty. Well, let's see if we can verify that. I disconnect that. And I remove that battery. The battery's out. And I'm just going to take this and hook it to the capacitor. 1, 2, 3, go. And it took about the same amount of time to discharge the battery as it took to charge it up. Okay, check on your neighbor, please. Check on your neighbor. Okay, I need my helpers again. Where are my helpers? Thank you. Oh, I'll get that. That one's yours now. Okay. Send those down the road. Need a helper over here. Where's my helper? Thank you. Okay. Okay, let's look at this. This is an old exam question. And if you look at the back of the sheet, that's another old exam question. And what you see is that there's 2 different flavors of RC circuits that I can ask on an exam. The one just has bulbs that are non-ohmic, and those questions tend to be more conceptual. Is the voltage going to be bigger than 6, less than 6, that sort of thing. If you turn the page over, you see that that's a very, very quantitative problem, where you actually have to give a number for the current through the battery when the capacitor is empty and when it's full. And the bottom line is, and folks, this goes in your toolbox. This is all you need to know about RC circuits. An empty capacitor acts like a wire or a closed switch. A full capacitor acts like an open switch, okay? And full is not always 12 volts. Full depends on the circuit, okay? Look away from the sun. So let's solve this problem together, and this will help you with your homework problem. We have 4 bulbs and a capacitor connected to an ideal battery. The capacitor is initially discharged or empty. You'll notice that the only times I can really talk about these RC circuits, there's 3 of them. We only talk about 2 in this problem. Immediately after I close the switch, when the capacitor is empty, and then a long time after the switch has been closed, when the capacitor is full. When it's empty, it acts like a closed switch. When it's full, it acts like an open switch. Now, if you turn the page over, you see that there's a part C, and that is, oh, I've had the switch closed for a long, long time. Now I throw it back open. Immediately after I open the switch, that capacitor is acting like a battery. But you have to figure out how many volts is that battery, okay? So in general, these problems have 3 parts. Right after I close the switch when the capacitor is empty, a long time after I've closed the switch when it's full, and then after it's been closed for a long time, I throw the switch open, and now the capacitor acts like a battery. Okay, let's do this one. What is the voltage difference across the capacitor? Well, that voltage difference is equal to the charge on the capacitor divided by the capacitance. Well, the capacitance for this capacitor was 1.5, but it's just a number. The key is that that's 0, and so the voltage across the capacitor is 0. Is bulb A brighter than, equal to, or dimmer than bulb C? Whoa, what do you think? Tell your neighbor. Which is brighter, A or C? Which is brighter, A or C?
None of them are.
I think they're yeah, no. Well, actually, no.
Okay,
No.
it's equal to, they are both shorted out. If an empty capacitor acts like a wire, if I put a wire across A, I clearly short out bulb A. But bulbs B and C are also in parallel with A. And so if A is shorted out and has 0 volts across it, so are they. So everything's shorted out. Now, if we look a long time after the switch has been closed, such that the capacitor is essentially fully charged, is bulb A brighter than, equal to, or dimmer than bulb C? Well, now the capacitor is acting like an open switch, and nothing goes down that path. And so now A is going to be brighter than C because current favors the path of least resistance. My students were putting that on their exams. It was 5 years before I figured out what it meant. Path of least resistance. Path of least resistance. Is the voltage difference across the capacitor greater than, equal to, or less than 6 volts? Well, if I know that the capacitor is parallel to A, it has to have the same volts across it as A. So the voltage across the capacitor is equal to the voltage across A. And I also know that the voltage across the A plus the voltage across D has to add up to the 12 volts of the battery. And I know that D is brighter than A. So that means that the voltage across A must be less than 6 volts. And so the answer is less than 6 volts. Okay. Let me just put some numbers here just for concreteness. If this D is 8 volts, A is 4 volts, and C is going to be 2 volts and B is going to be 2 volts. But the capacitor has to be the same as A, which would be 4 volts, which is less than 6. So there is a part C on this one. I was wrong. After the switch has been closed for a long, long time, such that it's full, we reopen it. Immediately after the switch is open, is A brighter than, equal to, or dimmer than bulb D? Well, now, what happens to bulb D? When I open the switch again, what happens to bulb D? It goes dark. It's on an incomplete path. And so A is going to be brighter because D is dark. Incomplete path. Is the voltage difference across the capacitor greater than, equal to, or less than the voltage across A? The same, because they're parallel. Okay, now there are 3 problems on your homework that are equivalent resistance problems. And let me get you ready for those problems so that you can answer those questions. You remember that when I have paths that are parallel, that are not equal to each other, I have to make them equal to each other. And I can make a 3 out of, well, first of all, I know that the resistance of this network is always going to be less than the least. So it's going to be less than 3. Now, I can make that 3 out of 2 6s. And now I've got 3 6s in parallel. I take the resistance of one path, 6, divide it by 3, I get 2. So 3 6s look like a 2 if they're in parallel. If I use V equals IR, that gives me 6 amps. Now, once I know the current through the battery, I go back and I ask, how is that divided between the 3 ohm resistor and the 6 ohm resistor? And that's one of the things I really, really like about this method of turning all of the resistors into the same size. Because now I know that when I take 6 amps, these are all the same resistance. So I'm going to send 2 amps here, 2 amps here, and 2 amps here. But then I remember that these 2 paths that have 2 amps and 2 amps are really the 3 ohm resistor. So that path is going to get 4 amps, and that path is going to get 2 amps. Or you could also just say, this path is twice as easy as that one. When I divide up the current up there, I better get twice as much this way as I have that one. Does that make sense? Now, this is a reminder. If I have a 1 ohm in parallel with 1,000,000 ohms, the answer is less than 1 ohm, less than the least. We saw that before. And that's because I can view this as a 1 ohm resistor with an extra path. Not a good path, but it's an extra path. Now, if I go back to that pop quiz there, I said that this looked like a 1 ohm resistance. Okay, well, where did I get that from? Well, again, I look for the lowest common denominator between 6 ohms and 3 ohms and 2 ohms. I know that my answer has to be less than the least or less than 2. The common denominator is 6. I can make a 3 out of 2 6s. And I can make a 2 out of 3 6s. And now, this network here looks like 1, 2, 3, 4, 5, 6, 6 6s. And so the resistance of that network is going to be the resistance of one branch divided by the number of branches, or 1 ohm. Okay? So I can reduce this circuit to a 4 ohm resistance and a 1 ohm resistance. And that means that I have to give 4 parts of voltage across this one for every 1 part I give across this one. Okay? Now, if you make orange juice, you put a can of concentrate into the pitcher, and then you put 3 cans of water into the pitcher. How many cans of stuff are in the pitcher? 4, okay? So if I need 4 parts in this box for every 1 part in this box, I got to divide up my 12 volts into 5 parts. And 12 volts divided by 5 is 2.4 volts. And so this one's going to have 2.4 volts, and this is going to have 4 times that, or 9.6 volts. See how I got those numbers? Now, we got 7 minutes. Let me help you with your homework. You're going to have 3 problems like that. 3 problems like that. And the first thing you're going to be asked is, what's the current through the battery? And then I can ask things like, what's the voltage across that 8 ohm resistor? Or what's the voltage across that 4 ohm resistor? Or how much current flows through this 4 ohm resistor? I can ask all sorts of questions about that circuit. But the first question you should answer is always, how much current is going through that battery? How much current is going through that battery? And so what you want to do is you want to reduce this circuit to this. One single resistance called the equivalent resistance. And in this case, I have an 18-volt battery. And this is how you do it. This is how you do your homework. You ask the same 2 questions over and over again in a round. What's in series? If you look up there in that messy network, do you see anything in series? Yeah, the 2 and the 4. Okay. Is this 10 ohm in series with that 4 ohm? No or heck no? Heck no. Yeah. The second question is, what's in parallel? Well, I got those 2 4s in parallel. Okay. And then once you've identified those, you redraw the circuit. You draw it all over again. The 2 and the 4, since they're in series, they look like a 6. 2 4s in parallel look like a 2. So I replace those. Okay. And I ask the questions again. What's in series? Well, the 10 and the 2. What's in parallel? Well, the 12 and the 6. Well, those aren't the same. I can't use my rule for equal parallel branches. So I make that 6 out of 2 12s. Well, now I got 3 12s in parallel. What does that look like? That's 3 times easier than 1 12. So that looks like a 4. And the 10 and the 2 look like a 12. Then I ask the questions again. What's in series? Well, those 2. and they look like a 12. 8 and 4 is 12. Then I ask, what's in parallel? Well, those two, they look like a 6. Well, now I can use V equals IR. 18 is equal to I times 6. That means my current must be 3 amps. Okay? Everyone with me? I don't want to lose you here. I can go back.
Please go
Raise
back.
your hand if you need to go back.
You go back.
How far?
I understand.
Right here.
Right here.
Yeah.
Okay? The 12 and the 6?
What is happening to the stick?
What's happening to the 6?
Yeah.
Well, I want to replace the 12 and the 6 by one single resistor. And it's got to, because they're parallel, it's got to be less than the least, and it's going to be 4. How do I get that? I turn them all into the same resistance. I know that I can make a 6 out of 2 12s, right? So I make the 6 out of 2 12s. And now all 3 of those 12s are in parallel. So I take the resistance of one path, which is 12, divided by 3 paths, 4. And then I make that into the 4. Is that okay? And then I add, are these two in series? Well, everything that goes through the 4 has to go through the 8. So they're in series. 8 plus 4 is 12. These are in parallel. So they look like a 6. Okay? Now, here's the important part. Once you get the current through the battery, you got to split it up between the branches. You have to split it up. Now, be the river. When the river gets here, remember all of this looked like 12 ohms. And all of this looked like 12 ohms. And so when it splits here, it's going to split 50-50. But when it splits here, it's going to split some other way. This path is harder than this path, twice as hard. Another way of saying that is this path is twice as easy. So it's going to get twice as much current. 1 amp's going to go this way, half an amp's going to go that way. Now, folks, V equals IR can be used locally. And you need this piece of information in your toolbox. We still have 2 minutes. If I want to know the voltage across this 12 ohms, I take the current that goes through the 12 ohms times the 12 ohms, and I get 6 volts. If I want to know the voltage across this 10 ohm resistor, I take the current that goes through the 10 ohms times the 10 ohms. So that would be 15 volts. If I want to know the voltage across this 4 ohm resistor, I would take the current through the 4 ohm resistor, which is half of that, or 0.75, 3/4 if you will, and 3/4 times the 4 ohms gives me 3 amps, or 3 volts. So I've got 15 volts here, 3 volts there, that gives me 18. I've got 15 volts there, 3 volts there, 18. I've got here 6 volts. I got a 1.5 volts going, 1.5 amps going through this one, so that's 12 volts. 6 plus 12, 18. Any path from one side of the battery to the other adds up to 18 volts of the battery. Okay? So once you have that current through the battery, you're all powerful. All powerful. Go somewhere else. Debrief. Thank you, Robert.
Oh, that went too